In this part, we're going to talk about a spectrophotometer that works a little bit differently than the other spectrophotometers that we've been talking about. And so this is the Fourier Transform infrared spectrometer, or FTIR, and we're going to look at this video will be about how the FTIR works. So originally, infrared spectrophotometers worked in basically the exact same way that we've talked about for UV-Vis spectrophotometers, where we have a broadband light source. We use a monochromator to select a specific color of light, send it through our sample, then have some sort of detector to detect the light. And so this image that I have here, this is actually a prism that was used in a monochromator back in the 1930s that was used for infrared spectroscopy. It was an image I found online. And so the reason it's made out of salt, sodium chloride, instead of glass or something like that, is that glass is opaque in infrared, and so you won't actually get any light through it. And so you have to build your optical components out of things that are actually transparent in the infrared, and salts in general are. Various kinds of salts are still used in infrared spectroscopy today. But starting in about 1970, the Fourier Transform infrared spectrometer was introduced. It was developed and built and sold. I think the first one was sold in 1969. And it's basically now the only type of broadband infrared spectrometer in use. There are laser-based infrared spectrometers, like the one I use in my research, but the applications for those are a little bit different from each other. So I actually went back and I managed to find in Analytical Chemistry, the journal, an advertisement for infrared spectrometers back from 1970. So this is that first infrared FTIR that was introduced, the Digilab FTS14. And so this advertisement is talking about how amazing it is, and they really are amazing in comparison. They provide a lot of advantages, so many overwhelming advantages, in fact, that you basically cannot buy a dispersive or your typical infrared spectrometer that uses a monochromator. And basically all infrared spectrometers nowadays are FTIRs based on the Fourier Transform. So we've mentioned this Fourier Transform. What is it? So on the next slide, I'll go over that briefly. Not in a lot of detail. It's pretty mathematically heavy to go through all the details of this. But we want to go over the general idea of what's going on. So the FTIR relies on the idea of a Fourier transform, which is that we can take some arbitrary function, like this, say, curve we have here. Maybe this is an absorbance spectrum where we have a couple of peaks that show up in our spectrum. And we can represent this with a sum of sine and cosine waves. And that's the Fourier series idea. And so we can take any arbitrary function, and if we have enough of them, if we keep adding more and more sines and cosines, we can get a very good approximation. And so this curve here on the left, we'll color in green today. So this curve on the left, we can represent by sums of sines and cosines. So if we just use, say, 3 sets of sines and cosines, we get something that doesn't really look like it, just one broad peak. As we keep adding more and more values to the series, we get something that approaches more and more closely to the actual, right? You can see the dashed lines here that are closer and closer to the actual function. And in the limit of having an infinite number, we get an exact replication. So, you can see even with 8, if we go up to n equals 8, we end up with a pretty good, we now have, 2 peaks. It doesn't line up exactly, but it's getting closer and closer. And as you keep adding more and more functions to this, more and more sines and cosines, you get something that's closer and closer to the real original signal that you had. And so the Fourier transform is a way of going back and forth between these our peaks that are represented here and this frequency representation where we have these sines and cosines at different frequency values. And so what these A and B coefficients tell you, right, this A sub n and B sub n, they tell you how much of your signal is happening at this specific frequency. And so if we have something that we measure, say, as a function of time, we can then say, well, how much of this signal over a function of time occurs at a frequency of, so many hertz? Or in the case of infrared spectroscopy, we measure frequencies in terms of wave numbers. At a specific wave number, where is my signal occurring? And so that proves to be really useful because it allows us to take spectra in the time domain, so measuring signal as a function of time, and then we use this mathematical function, the Fourier transform, to switch it into to figure out what's happening at specific frequencies, which is really what we're interested in when we're doing spectroscopy. We want signal as a function of frequency.